Okay, so today our main objective is to cover the concept of, again, assembly method. So we are going to start with the bagging. As we said earlier, we have bagging, we also have boosting, and also random forest. So the first question we are going to ask is, what are assembly methods? Right now, it seems like we have finished with all the supervised learning algorithms. We finish. So assembly method is not a new algorithm. I would say it's a new techniques or methodology that we can use. The goal here again is actually is right, is to increase accuracy. Is to increase accuracy. Also possibly for variance also, to reduce variance. To reduce variance. So assembly method are machine learning techniques. It's not algorithm. It's a machine learning techniques that will combine multiple individual models. Often we use the term the base learners, B-A-S-E, base learners. Or sometimes we use the term weak learners. Again, we will see as time goes on, to achieve a better predictive performance than could be obtained from any single model. So, for example, if you are doing a comparison, let's say we have some data and we decided we want to use a decision tree, let's say which one, C4.5. At the same time, I want to use the concept of random forest, which means the keyword is forest. Forests have more than one tree. And then apply these two algorithms in one data set, no matter how it is. A random forest always perform better than decision tree. At least if it comes to the worst, they may perform the same level, they may have the same accuracy, etc. But most of the time, again, random forest. So that's the main goal again. We use combination of models to increase accuracy. Example here, let's say we have a data set here from this diagram. We have a data set, a training data set. So what we do is that we break this training data set into, let's say, 10 sub-training data sets. So let's say we use the term, I'm going to use the term C1 to CT. We use the training data set again to create each, so the C1 will be a model, C up to CT. Then we have two options. Now, if we are doing classification, we are going to consider something we call the majority vote. Now, if we are doing regression, we are going to take average result as our class prediction. Again, we will see the method as, but that's the whole idea here. We have training data set, one big training data set. We break it into, let's say, 10 different sub-training, and we build 10 different models. Then we come up with the concept of classify to be based on voting, majority vote, regression will be based on, again, mean, average concept. Again, we are going to get more details on that soon. Now, here, as we said earlier, we use combination of models to do what? Increase accuracy. And as we said earlier, also, so many articles, or even I think the textbook also mentioned, the concept here also is very good if we have a variance problem, high variance, high variance. Yeah. Also, here we say combine a series of K learn models. Here we are using, let's say, the models we have up to K num, because we use K number of training data sets to build K different models. Now, with the aim of what? Creating an improved model, which will be M star. So out of C1 to CT, our goal is to get the best out. Yeah, that's why we say classification take majority vote, and then regression the mean. So the popular ones, as we said earlier, is the bagging, boosting, and also the summary method. Yeah. And in these lectures, we are discussing the bagging process. Yeah. So again, one more time is why we use assembly again, as we said earlier, to improve accuracy, but also we can reduce overfitting. So the concept of reduce overfitting here means it can help to generalize better. It will help to generalize better to unseen data. I would say to the unseen data, generalize more better. Also, it increase stability. Stability also can be increased. So in this case, we can In this case, we can say to be less sensitive to the specific training data or initial condition. Yeah. So let's wait for a few seconds, see if any question. As we said earlier also, primary used to reduce variance within a noisy data set. And also, as we said, it helps us also to avoid overfitting. And we mentioned unstable, so work best with unstable models. Unstable models, I would say the concept of high variance also is unstable, which means if we change a little bit of the training, it will give us different model altogether. Or let's see here, they say work best for unstable model, meaning models that are highly sensitive to small changes. So these small changes may occur in the training data set. A good example would be decision trees. And the concept of bagging was coined by Leo Bremer to refer to the following bootstrap aggregating algorithm. So in statistics, the concept here means we can do, we take a sample with what? Replacement. We'll talk about that as time goes on. So again, bagging stands for what? Bootstrap aggregating. And also it is an ensemble, I'll say ensemble, let me use the term mental algorithm. A mental algorithm designed to improve, as we said earlier, accuracy, avoid overfitting, also improve stability of a machine learning algorithms. Yeah. So again, the concept here, as we said earlier, is not algorithm, but it's rather machine learning techniques. And also, I think the primary also address, as we mentioned earlier, high variance in models. High variance. Primary used to reduce variances. High variance in model. And what is the whole core idea, or the whole idea, as we said earlier, is to train multiple or build a multiple models. So train a multiple independent based learners on different subsets of the original training data and then combine their prediction. That's the goal here. Now, somebody may ask, so what's the difference between bagging and boosting? We may use something like a doctor, let's say classification, let's say a patient have some problem and he visited, let's say, 10 doctors. 6 of them said they have disease A, 4 said they have disease B. So he may follow the one that said they have disease A, because that's majority. And this will be bargain. And in terms of boosting now, we have to assign weight. So what I mean now, let me use the same doctor's experience. Now, this time we are going to give, previously in bagging, we are assuming the doctors, they all have, the same qualification, the same, we didn't put any differences. But when it comes to boosting, we are going to apply weight to each individual doctor. Let's say the doctor that have a higher weight, it means he's doing good job. Maybe out of 100 patients he saw, he has only like 2% errors, so 98% good. Another doctor, maybe out of 100, he have 10 errors, so 90% good doctor. So now this means if two of them gave an outcome of a diagnostic, the one with the higher percentage, we're going to give him more weight than the one with the, let's say we even have a doctor who is 50-50. The chance that you get misdiagnosis is 50%, and that will get almost zero weight or very low weight. So this is with the concept of boosting, which we're going to discuss that. Okay, so how the bagging works, we are going to follow the steps here now. First, bootstrap sampling. As we said, the concept of bootstrap means you taking sample with what? Replacement. Sometimes, because of that, maybe sometimes we are not going, there will be some training, or let's say there will be some records in the training set that are not going to be used, how will I say, to be used at all. We are not going to use it. So that's the whole concept. So let's start with the bootstrapping sampling. After that, we get the sample data we need. So the next step now will be what? With each sample, we build a model. Then the third step will be what? Aggregation. For classification, as we said, we say majority voting among the K-based learners. K will be the number of learners we get. Or here also we say K bootstrap samples, how many samples we have. Regression means the final prediction will be the average of the prediction from the K-based learners. So first, let's go back and talk about what is a bootstrap. So here we say a bootstrap is as we mentioned, resampling techniques where a new sample is created by drawing, I will use the statistics term here, by drawing as observation with replacement. In sampling, we can do with replacement or without replacement. Here we do bootstrapping sampling is with replacement from the original data set. So here, let's say we assuming, let's assume we have an original training data set, let's say D, the size is N, great size is N, and we are going to, it depends. I mean, I'm going to make an example here. Let's say we are going to generate around 100 new training data set from the whole training data set. Now, each training data set will be used to do what? To create a model. And that will be the second step. Now, as we mentioned earlier also is that we may have some implication here. The implication here in the first step, the bootstrapping sample process, some records or some instances from the training data set will appear multiple times. It may appear multiple times in the number of sub training data set we have. And some instances from the original training set may not appear at all in all the sub training samples we have. So normally there's a term we use which we call it out of bag instances, or OOB, out of bag instances. Yeah, so I think that's all that's the only implication we can give. Let's say on average about it depends, but let's say 37 or 30 to 40% of original data points may be left out of a single bootstrap sample, which is the out of bag. This property is useful for again. Now, when we are evaluating the model, we may also consider to measure the out of bag error estimation. When we will talk about that hopefully in the future, in the coming. But the first thing I want us to get, if any questions about the concept of bootstrapping sampling. So, okay, so we have our sample now. So we move on straight to the second step, which is the base model training. So here, this is up to us. Again, here we are talking about general bagging. We give examples. So it can be decision tree, neural network, support vector machine, which one. So you train a separate base learner. You can use any algorithm on each of the number of K bootstrap samples we have. Then the base learners are typically of the same again type. So most of the time they will be the same type. I won't say more, yeah, most or majority of the time it should be the same type. Let's wait for a few seconds if any question, the second step. Now, the characteristics of a base learning, again, if you have a question, you can just speak, or anytime I hear noise, mute mic is on. I'm not going to mute any mic no more. Before I used to do that, I change. So if I hear the noise, I just keep quiet. And if I hear the noise for 1 hour, I'll just keep quiet for 1 hour. If I hear the noise for 3 hours, oh, then we just stay for 3 hours and go home. We all go home. So yeah, but I hope it won't happen like that. I'm just kidding. Yeah, so let's see. Okay, so the next will be the characteristics of the base learners. Here I can say that most of that, as we mentioned earlier, majority of the time they will be the same model. If you are using decision tree, preferable use only decision tree. If neural network, use only neural network. and they are often as strong learners. And we use the term strong learners in the sense that that they can fit the training data well, but again, it might suffer from high variance. A high variance example would be, let's say, unprone decision trees. Decision tree that is not yet prone, redundant. Yeah. And also each model is trained independently, must be trained independently. It's kind of giving us the idea of cross-validation method we use to test and supervise, where you break it to number of K folders, so then you check each one. So the same idea here, each model will be trained independently on their corresponding data set, the sample that they have, the bootstrap sample for each one. Let's say we represent it as D1 to, let's say, DK. So each D1 for M1, M1 will be our model 1. Do D2 for M2, then we get up to DK for MK. Yeah. So each model again, MK is trained independently on its corresponding DK bootstrap sample. So this independence allow for what we call a para computation. This can be done in para computation concept. So that will be the conclusion of step 2. So we move on to step 3 now. Now we have individual model created. Now we said if it's classification, so each base model MK predict a class label for the new instances. They are going to, let's say, for example, our classification here is to find out if patients have disease A or B or tested positive or negative for viral. Let's say by class. Yeah. So we get that. So now the final prediction will be determined by majority vote. If majority said, let's say we have 10 model, and 8 said this is A, only 2 said this is B. So for classification, we are going to use this is A then. So again, classification, the final prediction is determined by majority vote among the K-based learners. Among the K-based learners. Another example, let's say if 7 out of 10 trees predict class A, as we said, and 3 predict class B, then the final prediction is class A, majority. Now for regression, each base model MK predict, regression is a numerical value, it's a value. That's why we can, now classification, A, B, we can't do anything. Only thing we can do is counting. So that's why it's based on majority vote. But if it's a value, yeah. So here we get, let's say, all the 10 models, they all predicting the price of the stock price of a company, or a basketball height based on its weight or based on how it do scoring, it score in the game. We see that taller people score more than shorter people. I say taller people, taller players score more than shorter players. Just give some example here. So here then, we just find the average, get the average numbers together. So again, the final prediction is typically the average mean of the prediction from the K models, let's say 10 models. The price, each one price, we average all together. Some may be high, some may be low. So we put it in the middle. So example, we have 10 traits, predict values 10, 1, 9.8, 6, 8, 2. Just add all the value and divide by 10 and get the average. That's it. Yeah. So that's the process of how bagging works. Again, here we are not learning a new machine learning algorithm, but as we said, assembly method is about new machine learning techniques that we can use. The goal again is to improve overall performance in terms of lower the variance, increase the accuracy, stabilize the whole model, kind of things. So let's wait for a few seconds again, see if we have any question. If not, let's jump straight. Again, as I said earlier, if you have a question as usual, you can ask at any time. I'll just keep quiet. Not keep quiet, but, that's the way I speak sometimes. I just listen to you. English is my fifth language. So sometimes students misunderstood me. I sometimes use the word and I say keep quiet. No, listen. I listen to you, not to keep quiet. Okay. Yeah. English. Oh boy. Okay, let's keep going. So here we have a bootstrap aggregation. This is okay. So this is what I was giving. The example I was giving. Actually, I saw this example in a data mining textbook. That's one by Han Jilin or so. Yeah, data mine. Yeah. So yeah, they say diagnose based on multiple doctors' majority vote. As we said, that will be bagging. So yeah, get a set D of data posts. So in that textbook, Hanji, forget his name, but the author of the textbook here is based on his background is in database. So he always use the term tuples instead of saying observation or features or so he use tuples, we use that term a lot. Represent record, the number of records or observations in statistics. So yeah, we say given a set D of D tuples at each iteration I, training set DI of D tuples is sample with replacement. So that's bootstrap. Then a classified model MI is learned from each training set DI. Now, the step of classification, classify an unknown sample X. So each classified MI return is class prediction. The back classify M star, this would be the improved one, counts the vote and assign it. So this would be for classification. Then prediction can be applied to the prediction of continuous value by getting the average. So the goal often significantly better than a single classifier derived from the accuracies improve. As I said earlier, take decision tree, take random forest in the same data set. Always random forest will perform better. The worst case for random forest, maybe they will perform the same. Again, my statement that there can be a bias on what I'm saying, but majority of the time, that's how it happens. No machine learning, computer science, anything can happen at any time. So anything we say, we still have to put plus or minus 2 or 4 bias, minus 2 or 4% bias, like confidence interval. We always use 0.05 for the level of significance. Yeah. So, but majority of the time, as I said, random forests always perform better. If you look through a lot of articles, they may say that also. Yeah. So again, what is here is the same thing we discussed already, but I like the way this professor put it, and the author of this book, they put the steps down very straightforward, simple. Okay, so if no question, let's move on. Okay, so why does bagging work? So here we start with the intuition. So I think the first one, we mentioned all this already. No, we didn't mention diversity, but reduces variance. Yes. This is I would say this is the primary goal. The primary goal of bagging is to reduce variance. As we said earlier, I mean, you have a training data set. You build a model. Yeah, then maybe just take only one record, or I'll use the term one tuple. You have over 1,000 records, and you just take only 5 out of it. Use it to build a model again, then it give you different results altogether. So here we have a variance issue. Now, if we can break this training data into 10 sub-training and then build 10 different, either we average or we take majority, you can see the variance is gone. Now we mix everything together. So variance is gone. So individual-based model, especially flexible ones like a decision tree, always when it comes to variance issue, machine learning, decision tree is one of the very prompt to high variance here. Again, there may be bias there, but it shouldn't be more than 5%, like alpha 0.05. Yeah. So, like decision tree can have a high variance, as we said. This means that their performance can vary significantly, as we said, can vary significantly with the small changes in the training data set. These are also prompt to overfitting also. Yeah. So by averaging or even by taking the majority vote, the predictions of a multiple models trained on different bootstrap samples the errors or the fluctuations of individual models tend to cancel each other, as we said earlier, because now I have big one training data, I break it into two, and I not two, let's say 10, 100, and I find different model, and I average it or majority of it. You see, we miss everything together. So those small differences can cancel each other there. Yeah. Oh, I would say mathematically. Let's say mathematically, let's say if you have k independent random variables, the model prediction with the same variance, and the variance of their average will be the variance divided by k. K will be the number of models that we are going to build, or even the training data set that we're going to have. Why the models are not perfectly, I would say they are not perfectly independent. The bootstrap sample introduce enough diversity to significantly, I'll use the term significantly reduce of our raw variance. You see, because I have a variance, then I divide variance by k. K is the number. So, it will reduce it some way or the other. Yeah. I didn't make that up. Textbook also mentioned it. You can see it also in many articles. So this will lead us the concept of diversity, introducing diversity. So bootstrap sampling will make sure, or I'll use the term ensure, or make sure that the individual models are diverse. They are diverse because they are trained on slightly different subset of the data. This diversity is very important. Actually, that's the whole idea of reducing variance. If everybody, now, if all models were identical, then averaging their prediction, we get no result. It's like I have 220 and I want to find the average of 2. So I say 2 plus 2, 20 divided by 20 to give me the same 2. But so if there's any variance in the training data set can cause any variance. High variance, no, there will be variance, of course, but higher variance, then bargain is good to take that, or assembly method, that's in general. Assembly method is good to reduce that variance, as we can see. Variance is zero if everything is the same. I think statistics, that's what it teaches. To find a standard deviation of 3 values and the values are the same. The standard deviation is the same. The mean is the same. Everything is the same. So I think that's the main goal here. Let's wait for a few seconds if everybody agree with me. Then we move forward. Or not agree, if you have a question. I mean the same. Agree or have a question is the same to me. Again, as I said earlier, my English, just bear with me. Okay, so if no question, let's keep going. So here we have example, and here we are using again decision tree. So the problem is that decision tree, we already know they are very prone. So yeah, when it comes to high variance, always decision tree is always mentioned. Yeah, and high variance mean overfitting. So we decided a solution. Let's do bargain with decision tree. So we train many dependent decision trees, each on a different bootstrap sample. Again, bootstrap sample means taking a sample with replacement. For a new input, each tree makes a prediction or classification, either one. Combine the prediction. If it's majority vote for classification, if it's regression, average for regression. The result you get 100% sure, a more stable and often accurate model than a single deep decision tree. Actually, they use the term deep here. A deep decision tree will be unpruned tree. Unpruned tree. No, unpruned tree means it will be very long, deep. No, machine learning, they come with a lot of terminologies. Okay, so let's wait for a few seconds, see if any question on this. Okay, let's keep going. Oh, okay, so this is visualizing the bargain, as we said earlier. Original training data set, we break it into n sub-data sets. What we're going to do, as we said earlier, we use the bootstrap sampling. We have n to n data points from 1 to n. We break it And we use a bootstrap sample with replacement, sorry, not without, with replacement. And then here we have 4. Let's say K. So we have 1, 2, 3, K up to K. Let's say 4. So 4 samples, we are going to build 4 models. So we have 4 models. Then we aggregate it. Aggregate means combine. So if it's classification, we use voting as we said. If it's regression, we take the average. Then we get our final prediction. Yeah. Let's wait a few seconds if any question. Okay. So what are the advantages of bagging? Yeah, so we have few advantages here. And most of these advantages, we mentioned all of them already. First, we say, well, let's start with, say, reduce overfitting. It's same concept as reducing the variance. So I would say that effectively mitigate the problem of high variance will lead to a model that will generalize better to unseen data. Put it, so I can put it that way. Or here we say by averaging or voting across multiple models trained on slightly different data, bagging can effectively smooth out the predictions and reduce the impact of noise in the training data. This will lead to more robust model, reduce variance, or even reduce the overfitting. A robust model will also surely reduce overfitting also. Yeah. The next one is the common one. I think the two, variance and accuracy. So improve accuracy. Reduce variance, increase accuracy, often result in a noticeable improvement in predictive performance compared to single base model. Again, take a decision tree. It can be any type, C 4.5, anyone you think. Then take random forest. They are all decision tree concepts. They all use decision trees. Random forest will do better because you have more than one tree. You can even build as many as you want based on the training data set. So that will be one of the disadvantage. No, again, we'll come to the disadvantage. Like what I'm going to say is that since we are building so many model computational costs, so to take time, it will consume more resources because you are building different models. But we'll come there. So parallelizable or parallelization, or yeah, they say parallelizable. Yeah, also that's another. So conceptually straightforward and easily implemented. That's simplicity also. The independent training of base model make it highly, I'll use the term amenable to para processing. Good for para processing, maybe in short. Simplicity, simple to implement, as we said. Handles overfitting. Yes, if we can handle reduce variance, that will give us a good news to reduce overfitting. Overfitting means what? We have a training data set to do one thing. Next time we bring a test data, it can do better because it based on his knowledge on the training. The training was too much for him, for the model. So, and that can have effect. Yeah, so, yeah, we'll talk about the evaluation of. Actually, we even have a special lectures for that evaluation of classification model, supervised models, both classification and regression. That will be a lecture by itself in the future. It should be next week, if not today. Okay, so I think that's it. If no question, let's move on to disadvantage. So you can see the last one is the most computationally cost. It's increased computationally cost. Training K-based model can be computationally very, very expensive or more expensive. Not only that, time consuming also. Time consuming than training only one single model, especially if the base learners are themselves complex. Let's say I'm using neural network support vector machine. The process itself is already long process, especially if it's nonlinear concept that have to be improved to linear, take higher dimension, etc. That will take a long time. And this time you have 100 support vector machines to train. then either you take majority vote or the mean. So to take time. Yeah. And also no bias reduction. See, as we are talking, we didn't mention about reduction of bias. We didn't mention that. As mentioned, bagging is not designed to reduce bias. So if the chosen base learner has a high bias, most likely the bag assembly will also have a high bias. The major design for assembly method is again increase accuracy, reduce. I won't even say the major one should be the. I mentioned it many times, almost it's gone again. The term is not coming. Uh, for example, come here right now. Or somebody can remember. We mentioned it. Variance. See, it's almost gone. Because if you have a training data set, as we said earlier, 1,000 records, and I remove only 3, and I build a model, and the model change. I mean, 3 out of only 1,000. Then that's a very high variance. And that's what we mention. All our lectures is based on when we talk about sampling method. So if this training set, I break it into 100 and train different 100 model, average it all based on majority vote, we can say it will cross out the high variance issue. If it doesn't even remove it, at least it will reduce it totally down. But in terms of bias, no. Okay, so no question. Let's keep going. Okay, so right now we are not going to talk about random forest, but just we put some few things here that the whole concept here can lead us to idea of also using what we call the random forest. Random forest is bargain. So a very popular and powerful, see, that's a very popular and also powerful extension of bargain. It's random forest. Random forest, why we use it a lot? Because as we said earlier, an algorithm like neural network or support vector machine or even probabilistic methods like Bayesian, etc. We don't really mention much about their high variance. When we talk about high variance, the first thing that comes, so again, I can be 4 to 5% bias here, but most of the time it's decision tree. So the book everywhere. Now, random forest is decision tree. This time we build as many decision trees as we want using the same concept bargain uh, method or bootstrap. Let me say bootstrap sampling, bargain. Yeah. So using decision tree as a base learner, the random forest had extra layer of a randomness when splitting the node, and it will consider a random subset of features like feature bargain and further decorrelating the trees. And this is the most straightforward application. Let's wait for a few seconds if any question. Yeah. The only thing I can mention here, I would say in terms of random forest, again, we're going to cover that. We have a lecture slides for that also by itself. So the next section is when to use bargain. So they gave us many examples, up to 5 different ways we can use it. I would say we mentioned the advantage. So something that will go against the advantage, I think we can say that would be a good one. So maybe I will can say that when your base model are prone to high variance, I think that's, advantage is to reduce the variance. So this is the ideal scenario for bargain. Example include an unprone decision tree, which we say the deep decision tree, very high variance. And also complex neural network is possible, or k nearest neighbors when k is very small. If you remember, we talk about k nearest neighbor. When the K is very small, the variance can be high. And when it's too much too, it's a problem. So we have to balance the K value for K nearest neighbor. Also, another option given here, look at the slide, is when you want to improve stability. And remember, we use that as an advantage. Also, robustness of your model. So if you want to improve the robustness of your model or the stability, it's good. Because if your single model performance changes, fluctuates significantly with slight changes in data, the bargain can help. So high variance lead to what? Unstable system, leads to bad stability of the model. So you can see how the whole thing works. Everything fitting very perfect. Next, also, as we mentioned earlier, when the computational resources are available, remember that was the disadvantage. Computationally very expensive. Yeah, very expensive. So if you have the computer resources, then it's a good one. So that's all we can say here. Let's see if we have any question before we move on. Okay. So what are the key takeaway? Well, I would say that, no, I shouldn't say I. We would say that bargain is a powerful and also the widely used assembly method, which even leads us to random forest, the most common one that is used. And also it leveraged the bootstrap sampling and also the aggregation to significantly reduce variance of a base learners, leading to what? More accurate and also what? Robust predictive model. It may increase, or I would say that why it increased computational costs and also reduce interpretability. Decision tree is the most simple algorithm that can be interpreted. I mean, you just follow the rule to the leaf. You can even get the rule, you know what is. But it will increase the simplicity of interpretation of the model. But the benefit in terms of improved performance, particularly when dealing with high variance model like deep decision tree, make it more better. We don't have no choice there. Bargain is very good. Yeah. It's a good tool in machine learning. The practitioners took it. Yeah. And also, we can use the waker if we have time. So sometimes so far this class, nobody asks before. Sometimes as time goes and student may ask, oh, so how can we implement this? I said, okay, hold on, let's use Waker because we don't have no time to write the coding. So Waker, we can select it's just plug and play. Maybe some of you know. So hopefully today, if we have time, we can try the random forest concept or any of the bargain method using Waker to see how it works. Okay, so that will be the conclusion. So let's wait for a few seconds, see if any question first. Again, as I said, the attendance, I'm not going to call it maybe like 10 minutes to the time we leave. It has been a very good method for me. I prefer teaching, spending 3 hours teaching than to spend, no, not 3 hours. I prefer spending 2 hours, 15 minutes in teaching and break than to spend 30 minutes alone in attendance. And, yeah, so that's why it's better. Unfortunately, not unfortunately, in our institution policy, we have to take attendance. It's required. So we have to. Okay, so it seems like there's no question. So I'm going to stop this recording now. And the next class, we're going to move on to boosting. We'll record also. So right now, just